Quantum circuits are basically composed of inputs, and in our case, we call them not qubits, but wires, right? So each one of these horizontal lines, we call them a wire instead of a qubit. You'll see that other libraries call them qubits, but it's the same thing. You prepare initial state, and you have some gates in it. The gates in PennyLane might be called differently than in other libraries, but they are the same. So that is something that is useful to know. And at the end, you have measurements. And all of this is basically linear algebra. That is what allows us to be able to apply the tools that we know from linear algebra in quantum computing. So now, differentiable programming, I mentioned that you could differentiate over an entire circuit, and you can also use it with parameters, right? So you have some inputs, let's call them X, and you have some parameters in your gates, and you can optimize over those parameters. So one of the issues we have, for instance, is about creating adding an SPSA optimization method. So if you already know a little bit about optimization, you're probably going to like to try out that bounty issue that we have. Actually, let me try to share. I think I can't share. I can't switch between tabs, but you can definitely go to the PennyLane GitHub, and you can see it. Maybe I can share my entire screen in a sec. You can compose it with classical circuits as well. So if you want to try out classical and quantum together, this is a very good opportunity. It is very flexible, so it allows you to do do things at your style. And we like that, the modularity of PennyLane. And we also have something called a keynote, which is just something that englobes like everything that happens quantum inside of this keynote. If you're gonna work with PennyLane, you're probably gonna understand more of how it's written, and it's a very good opportunity to learn about different topics, right? Not only quantum, but also software development. I think hackathons like this one are very good for that. And you will be part of PennyLane. You will be listed as a contributor, and you will know forever that you created a part of PennyLane, which is exciting. You can do, for instance, variational algorithms, which is something that we usually use a lot when we start learning about quantum computing. And this leverages a lot the fact that you can have differentiable quantum computing. You can find the gradient over that computer and just modify your parameters until you find the best ones. You can find us on YouTube, on Twitter, on LinkedIn. We have a newsletter for Xanadu. And also, so I'm gonna